7 cosmic visitors are heading toward Earth. It's a headline that sounds impossible, yet it's actually happening. By late 2025, 7 large comets will gather in the inner solar system over just 6 months. This is an event so uncommon that top surveys like Pan-STARRS and Atlas have recorded nothing like it. And nestled among them is 3I Atlas, just the 3rd interstellar comet ever spotted. With its strange chemistry and huge green coma, it's the ultimate cosmic wildcard. The chances of this occurring randomly are less than 0.5% per decade. Is this simply an astronomical fluke, or are we witnessing something that defies the rules of our sky? The answers, along with the risks, begin now. Each night, a quiet network of digital eyes scans the heavens. They are the planet's automated comet finders, Pan-STARRS Atlas, and others like them. Positioned atop remote mountains in places like Hawaii, Chile, and South Africa, these telescopes survey almost the whole sky every single night. They capture faint flickers that even the keenest human eye would miss. Their cameras can detect objects down to magnitude 21, much dimmer than Pluto ever looks from our world. Every picture is a mosaic holding millions of stars and galaxies, but what truly matters is motion. A lone pixel drifting between frames reveals that a new comet is present. This process is non-stop. Pan-STARRS and Atlas work on a schedule that scans the majority of the sky every 2 to 3 nights. Their software checks each new image against a digital map of the universe, marking anything that has moved. The moment a candidate shows up, a chain reaction kicks off automated alerts, quick follow-ups from telescopes globally, and a sprint to verify the find before it vanishes into the noise. This digital watchfulness has completely changed things. 2 decades ago, finding a comet required months of patient observation and some good fortune. Today, the number of discoveries has nearly doubled each year. Dim, faraway visitors that used to go unseen are now recorded, monitored, and studied in real time. The Minor Planet Center registers every detection, creating a census of these icy travelers that expands by the hundreds. Yet, despite all this capability, even top surveys seldom spot more than a few bright comets in one season. This cluster of 7 major comets in late 2025 is straining the capacity these systems were built for. Engineers and operators who typically let the algorithms work on their own are now fixated on their screens, watching the data feed ignite with more comet alerts than anyone ever imagined was possible. Now, for the very first time, the machines are finding it hard to keep pace with the sky. Before we get deeper into this cosmic traffic jam, a quick reference guide is helpful. The science of comets has its own terminology, but most of it is simpler than you'd think. Perihelion is just a comet's nearest pass to the sun. This is the point where the sun's light goes to work, transforming a frozen core into a spectacle of gas and dust. There's a reason this word appears in every comet forecast. It's where the real show begins. Since distances in our solar system get large quickly, astronomers use the astronomical unit, or AU for short. 1 AU is the Earth-Sun distance, roughly 93 million miles or 150 million kilometers. So, if a comet has a perihelion of 0.25 AU, it's a fourth of the distance from the Sun to our planet. For observers, a closer comet means better chances for a brilliant show. When it comes to brightness, astronomers rely on the magnitude scale, and here is the secret: lower numbers equal brighter objects. A magnitude of 6 is about the dimmest thing most people can spot without any help under truly dark skies. A magnitude of 2 or 3 is bright enough to grab the notice of anyone stepping out at sunrise or sunset. With a bit of luck, some comets can even shine brighter than the most brilliant stars. Then we have the issue of tails. As it approaches the sun, every comet develops at least one tail and occasionally 2. The dust tail is wide and faint, composed of microscopic grains propelled by sunlight itself. The ion tail is narrow, straight, and blue, formed from charged gas carried directly by the solar wind. You can picture it as a space weather windsock. Once in a while, a solar storm can sever this tail completely, only for it to grow back within hours. While these tail disconnection events are uncommon, with this many comets in the inner solar system, 2025 might offer more than one on camera. Remember these fundamentals. They will help you understand every headline, navigate any sky chart, and appreciate every surprise these 7 visitors have waiting. Statisticians analyzing comet data sometimes say the universe is cheap with its surprises. During a normal 6-month period, the chances are we'd see 2 or perhaps 3 comets that are bright enough for a backyard telescope. The others are dim, far away, and bound for the Minor Planet Center's archives. However, late 2025 completely shatters those expectations. 7 major comets, all reaching perihelion within a single 6-month window, have triggered alarms in every Monte Carlo simulation from comet population modelers. The figures are dramatic. In the past decade, digital surveys have elevated the detection rate of faint comets to incredible new levels. Still, even with our best tech simulations, reveal a 7-comet cluster in one season is a statistical anomaly. When scientists input actual survey sensitivity and comet population data into their models, the average expectation is only 2 or 3 in a 6-month span. The probability of 7 is below 0.5%. Some simulations produce odds nearer to 1 in 1,000 years for a cluster this bright. This rarity isn't simply due to better cameras or more watchful software. Bright comets are dictated by the physics of their orbits and the sheer chance of when they are nudged toward the sun. Survey efficiency helps find more faint wanderers, but it can't just create a group of 7 major visitors. The 2025 group is unlike anything seen in the digital age, and even older photographic records show no parallel. For data scientists, this is the type of anomaly that requires a closer investigation. Are we witnessing the aftermath of a faraway collision, a strange fluke in Oort cloud dynamics, or a cosmic coincidence so unusual it almost seems planned? No matter the reason, the data is clear. The 2025 Comet Jam is the closest modern astronomy has ever gotten to hitting the celestial lottery. Some comets pass through the solar system almost without being seen, their dim glow swallowed by the backdrop of stars. Of the 7 2025 visitors, 2 belong to this quiet group: C 2022 E3 Pan-STARRS and 240P NEAT. Pan-STARRS hits perihelion on July 31st, swinging in at roughly 3.82 astronomical units from the Sun, far past Mars and nearer to Jupiter's orbit. At such a distance, sunlight barely affects the icy surface. The outcome is a small coma, which is only visible with telescopes that have sensitive detectors. Most home observers will only see a faint smudge even during the clearest nights. 240P NEAT, another repeat traveler, makes its pass on December 19th at 212 astronomical units. That is still double the distance from the Sun compared to Earth, and the brightness reflects that. This comet has completed the trip before each time presenting a subtle encore for anyone willing to hunt for it in the winter sky. For both of these objects, the primary audience is a committed group of amateur astronomers who log observations, stack their images, and share notes online. Their dedicated work helps complete the faint end of the comet census, making sure that even the most silent visitors get counted. While these particular 2 comets are not going to be in the spotlight, they are a reminder of the full range in the 2025 lineup. From faint telescopic whispers to major headline makers, their appearance sets the scene for brighter, more exciting arrivals yet to come. For anyone who's looked up at night and wished for a comet as bright as the stars, late 2025 brings more than just a glimmer of hope. 3 of the 7 visitors, Swan Atlas, K1, and Lemon, are poised to be genuine crowd pleasers. each one carrying its own promise of a spectacle. Swan, with the official name C25R2, comes in for its nearest pass to Earth on October 21st, flying just a quarter of an AU away. That's around 37 million kilometers, near enough for the solar wind to stir up an impressive tail, and bright enough that even casual observers might see it at dawn with their naked eye. Outgassing models are predicting Swan could hit magnitude 2 or 3, a brightness that makes Comet watching a true neighborhood event. Only weeks after Atlas K1 rushes in, hitting its perihelion on October 8th, deep inside Mercury's orbit, the powerful sunlight at 0.33 astronomical units will likely send its activity into overdrive, releasing strong jets of gas and dust. Astronomers are anticipating a massive tail and the sort of unpredictable eruptions that create headline-worthy photographs. Next is Lemon C2025A6, making its closest approach on November 8th at slightly more than half an astronomical unit from the Sun. Projections indicate it could brighten to magnitude 4, perhaps 3.5, which would make it visible at dusk in the northern hemisphere, and a perfect target for backyard binoculars. Every one of these comets has a unique energy. Swan's near approach, Atlas K1's inner orbit spectacle, and Lemon's classic evening appearance all give us a chance at something special, a comet so bright you won't need a telescope to see the show. Not all comets in the 2025 lineup are best viewed from Earth. Some, like 414P stereo, are almost invisible to backyard telescopes, but are perfectly positioned for a fleet of spacecraft orbiting the Sun. On September 27th, 414P will pass just over half an AU from the Sun, which is closer than Venus. However, its orbit positions it within the Sun's glare from our perspective. This is where missions such as SOHO and Stereo step in. Their cameras, built to watch for solar storms, can catch comets as brilliant streaks in the solar corona, showing details about their activity that ground-based viewers would miss completely. Mission teams at both NASA and ESA are already rearranging schedules, deciding which comets will get valuable instrument time. The October sky will be busy not just with the comets themselves, but with competing scientific priorities. Swan and Atlas K1 are promising dramatic tail displays, while 3I Atlas, the interstellar visitor, requires careful observation during its quick pass. Each spacecraft has a very limited field of vision and is only able to point at a single target at once. That leads to hard decisions. Should they focus on the unique interstellar chemistry of 3I Atlas or follow the changing tails of Swan and Atlas K1 as they react to solar storms? Heliospheric imagers and coronagraphs will be tracking tail disconnection events in real time, capturing the exact moment a solar eruption cuts off a comet's ion tail. These observations are not merely for looks. They show how the magnetic field of the Sun shapes comet tails, and by extension, the invisible space weather that permeates our solar system. In 2025, spacecraft and ground-based telescopes will create a coordinated network. Each will cover the angles the others cannot, ensuring that not a single visitor passes by without being studied. 7 comet arrivals are all packed into a single stretch of the calendar. From late July all the way through December, the inner solar system will become a cosmic highway. The very first visitor, Pan-STARRS, makes its distant pass in July, barely registering on the detectors. After that, the pace picks up. By September, Swan is approaching, followed right after by 414P stereo, which flies by the Sun as spacecraft fight for position. October gets very crowded. Atlas K1 plunges toward the Sun, outgassing intensely inside Mercury's orbit. Mere days later, 3I Atlas, the interstellar anomaly, traces its hyperbolic route past Mars, its coma expanding to hundreds of thousands of kilometers wide. Lemon comes next in November, appearing in the dusk sky with the potential for naked eye brightness. Finally, in December, 240p neat completes the series, a quiet finale for those still watching. When placed on a timeline, these arrivals seem less like a random collection and more like a cosmic signal. Each comet's perihelion occurs within weeks of the last, which leaves very little rest for astronomers or for skywatchers. The tight schedule results in overlapping observation campaigns, packed data pipelines, and a continuous flow of new images. For once, the difficulty isn't in locating a comet, it's in knowing which one you are looking at. This 6-month compression transforms the sky into a living laboratory where the mechanics of the comet tail and solar wind are demonstrated in real time, occasionally with several comets visible in the same frame. The stage has been set for a season of tail physics and solar spectacles unlike anything seen in recent history. Every single comet in the 2025 lineup will bring a unique feature to the night sky, but nothing will be more prominent than the twin tails that stream behind them. The distinction is all about what is being pushed and what is doing the pushing. The dust tail is wide and curved, formed by microscopic grains that are swept from the comet's surface by the force of sunlight. These tiny particles scatter the sunlight in every direction, which gives the dust tail a pale, sometimes golden, luminescence that can extend for millions of kilometers. It spreads out softly behind the comet, tracing the curve of its orbit like a glowing wake. The ion tail, however, is a straight, thin blade of electric blue. This tail appears when ultraviolet radiation from the sun removes electrons from gas molecules in the coma, which turns them into ions. The solar wind, a flow of charged particles streaming from the sun, then grabs these ions and flings them directly away, regardless of the comet's direction of travel. The outcome is a tail that consistently points straight away from the sun's position, often with a much sharper edge and more intense color than the dust tail. For skywatchers, the visual differences are obvious. Dust tails are broad, soft, and usually yellowish or white. Ion tails are thin, straight, and blue. Each tail offers a different story about the forces that are at work, and both are susceptible to the sun's changing moods. When a solar storm passes through the ion tail, can get sliced off in an instant, an event that shows just how incredibly dynamic and unpredictable these cosmic visitors truly are. Solar storms do more than just illuminate the auroras. They can transform a comet's elegant tail into a complete battleground. When a massive coronal mass ejection, or CME, rushes through the inner solar system, it pulls the sun's magnetic field with it. If a comet is unlucky enough to be in the path, the effects can be absolutely breathtaking. The ion tail, that straight blue streamer pointing away from the sun, can be completely severed in just minutes. This is not a slow fade or a gradual disintegration. One moment the tail is millions of kilometers long, and the next it's been cleanly sliced off, left to drift in space as the comet generates a brand new one. The most well-known instance occurred in April 2007 when NASA's Stereo spacecraft observed Comet Encke during a disaster. A CME struck Encke's ion tail, ripping it away in real time. That footage turned into a case study that is replayed in heliophysics seminars and comet watching forums. Scientists refer to these events as magnetic reconnection, a sudden rearrangement of magnetic field lines that pulls the tail's ions out of their alignment. For a couple of hours, the comet remains exposed, its tailless condition a clear visual marker of the sun's unseen power. With 7 comets packed into the ecliptic in late 2025, the chance of seeing another live tail snap is higher than it's ever been. Heliophysicists and amateur astronomers are both on high alert, looking for the classic signs: a sudden bend, a break, or a faint wisp that gets left behind. Each event provides a front-row view of the sun's immense reach and a reminder that space weather isn't just a theory, it is visibly written across the sky in real time. Comet tails are not just for taking pretty pictures, they also serve as immediate space weather updates. The reason is geometry. In late 2025, the majority of the 7 comets are following paths near the solar system's ecliptic plane, the very same flat sheet where Earth and the other planets orbit. This common highway means that whenever the sun unleashes a coronal mass ejection, or CME, the probability of a comet being in its path increases dramatically. It's just a matter of simple alignment. With so many comets grouped near the ecliptic, they each spend much more time in the direct firing line of solar storms. Forecast models from heliophysicists show the numbers plainly. In a standard year, a bright comet might have a 10 to 20% probability of a visible tail disconnection near perihelion. With 7 comets lined up along comparable orbital paths, those chances multiply. Statistically, the 2025 season may produce several tail snap events and possibly even 2 or more within the same week. For skywatchers, this is about more than just a busy sky. Every CME that travels through the inner solar system is like a roll of the dice. If the timing is just right, the sun's magnetic field will cut through a comet's ion tail, creating a sudden break, a visual signal that space weather has just struck. With this many comets in perfect geometric position, the next few months promise a rare opportunity to see the sun's invisible hand at work, written in blue streaks across the dawn and dusk. The data coming from the world's most powerful telescopes is incredible. Astronomers working with the Hubble Space Telescope and the James Webb Space Telescope have clocked the coma of 3I Atlas, its glowing cloud of gas and dust at almost 700,000 kilometers across. That is not a misprint. This one comet's coma is nearly half the sun's diameter and over 50 times wider than the planet Jupiter. Images reveal a hazy greenish sphere that completely dwarfs the rocky nucleus inside, a tiny piece lost within a cloud that could engulf entire planets. But the size is just one aspect of the story. What really makes 3I Atlas stand out is its activity level. As the sun's light hits the surface, jets of gas and dust shoot from the nucleus with unbelievable force. Data from JWST and ground-based observatories place the dust ejection rates at 6 kilojoules for small grains, about a bowling ball's weight every second, and as high as 60 kuas for bigger pieces. These jets form fans and streamers inside the coma, which sometimes change from hour to hour as new vents are opened and closed by the nucleus's rotation. The outcome is a dynamic living structure. The result is a living, breathing structure constantly reshaped by sunlight and space weather. Imaging teams from Gemini South and Palomar Observatory have spent countless nights tracking these changes, stacking exposures to tease out subtle details in the jets. Their work reveals a comet that is anything but static. The jets flicker and pulse, sometimes tracing arcs hundreds of thousands of kilometers long. Each eruption delivers fresh material into the coma, which feeds the tails that extend far behind it. Even from a distance of over 1 astronomical unit from the sun, 3I Atlas is putting on a performance that matches some of the most active comets ever witnessed. The sheer scale of this physical presence is difficult to comprehend. For astronomers, it is a rare opportunity to observe the mechanics of cometary activity in real time with some of the most advanced tools ever created. Every new image and every measured jet contributes another piece to the puzzle, setting the stage for the next major question: what is this visitor actually made of? What occurs when a comet from a different star system shows a chemistry that nobody anticipated? Spectroscopists working constantly with JWST and Sphinx have discovered that 3I Atlas is a true rule breaker. Unlike the majority of comets where water vapor is the main attraction, this visitor's coma is inundated with carbon dioxide, and the numbers are impossible to overlook. For each molecule of water, there are 8 of CO2, an 8-to-1 ratio that establishes a new record for any comet that has been measured to date. The standard script for a bright comet is water ice should be front and center, vaporizing as sunlight hits it and creating the classic glowing tail. But with 3E Atlas, water is practically an afterthought. Instead, CO2 jets are erupting from its surface, coloring the coma green and sparking a debate among planetary scientists. Was this comet created in a frozen region far beyond its home star's reach, where carbon dioxide could freeze in large amounts? Or is a thick insulating crust concealing pockets of water ice that are just waiting for the perfect time to erupt? The answer is not yet known, with teams studying every spectrum to find the truth. This particular chemistry isn't simply an academic point of interest. If 3E Atlas is ejecting CO2-rich dust, the particles that it leaves in its wake could be unlike anything our Earth has ever encountered. And a new twist is coming. N-body simulations indicate that after its perihelion, the dust trail from this interstellar visitor might actually cross Earth's orbit in the middle of 2026. Meteor scientists are already charting the potential intersection point, creating plans for radar and airborne missions to capture even a single particle of genuine interstellar dust as it incinerates in our atmosphere. If they succeed, these efforts could provide the very first direct sample of material that was forged around a different star, a chance to study isotopes and molecules untouched by our own solar system's history, a chance to analyze isotopes and molecules untouched by our own solar system's history. For now, every new observation of 3I Atlas is a pass to the frontier of planetary science, where the stakes are truly nothing less than rewriting what we understand about the chemistry of worlds beyond our sun. Rumors are known to spread faster than comets. In the weeks before the 2025 Comet Parade begins, social media feeds are filling up with warnings, dramatic allegations, and a constant flow of doomsday scenarios. But this is what the actual data shows. Every comet in the 2025 group follows a precisely mapped trajectory, calculated and recalculated by professional astronomers who are using the planet's largest telescopes and the Minor Planet Center's international database. None of them come anywhere near intersecting Earth's orbit, much less present any risk of a collision. The closest flyby by Comet Swan will be at about 37 million kilometers away, over 90 times the distance to our moon. All the rest will pass even farther away, their paths bending smoothly around the sun, influenced only by gravity and nothing else. Expert panels from NASA, the European Space Agency, and other independent research organizations have all reviewed the orbits, checked for any potential disturbances, and have published their results in open access journals. Their conclusion is unanimous. There is no known physical way that this comet cluster could set off earthquakes, storms, or any of the other disasters that are currently trending on the internet. Gravity operates just as it always has. Comets are simply icy remnants, not cosmic demolition balls. The only thing they will probably influence is the number of people who are looking up at the sky during dawn and dusk. The message here is simple. This is an amazing sky show, not a real threat. The very best way to enjoy it is with a feeling of wonder, not with worry. For anyone who is excited to see a comet for themselves, the next thing is to know exactly where and when to look. Go outside on October 21st, right before sunrise, and you may just see the sky's main attraction. That morning, Comet Swan will make its closest pass to Earth at about 37 million kilometers away. You won't need a telescope if you have dark skies and a clear view of the eastern horizon. Look low toward the east just a bit before dawn. If the forecasts are correct, Swan could shine as bright as magnitude 2 or 3, competing with the brightest stars. Its tail, which is sculpted by the solar wind, might stretch over a large part of the sky, a fantastic treat. for anyone who is awake early enough to witness it, a few weeks after the dust sky gets the spotlight. From November 6th to the 12th, Comet Lemon will glide into view in the western sky right after sunset. This is your classic evening comet, so there's no need to get up early. Just locate a place with a broad, clear view to the west. Lemon could get to magnitude 4, maybe even brighter, if its activity picks up. In rural areas, that is bright enough for the unaided eye. If you're in town, binoculars can help you spot the fuzzy glow just above the horizon. The ideal time is 30 to 60 minutes after the sun sets before the comet gets too low. For either of these events, a pair of binoculars will reveal more detail, showing the comet's gentle glow and the very first signs of a tail. A small telescope can take you even further, showing structure within the tail and some subtle shifts in color. But you don't really need any fancy gear. A printed star chart, a phone app, or even just a compass can point you in the correct direction. Remember to dress for the weather. Bring a friend along and allow your eyes some time to adapt. Your patience will be rewarded. Comets can often brighten or fade without warning, and the view itself changes from one night to the next. In a year where the sky is providing more than its usual share of amazing surprises, these observation windows are your personal invitation to take part. No prior experience is needed. The only thing truly required is the decision to look up. These clustered arrivals have no known parallel in more than a century of comet observation records. Scientists have noted that while the dust trail of 3I Atlas might cross Earth's orbit in 2026, there is no impact risk according to all published orbital models. However, the reason so many comets are appearing in a single season is still unsolved, with current population models being unable to explain this particular spike. The existing evidence suggests a rare convergence that has been shaped by a combination of random luck and our improved detection capabilities. As 2025 and 2026 play out, the official record will document not just a statistical anomaly, but also a unique chance for observation and scientific discovery, all chronicled in real time for any future analysis.